Welcome friends to the Home Academy. Today we will discuss deflection of the beam. Before discussing deflection of the beam, let us understand what is bending what is the function of the beam. Let us consider a beam. A transverse load is acting on that beam. The load is acting on the beam in the transverse direction. As a result, the beam transfers that load into the column. So beam transfers the transverse load into the column. When the load is applied on the beam and we draw the free body diagram, it will have the upward shear force and the bending moment. Because of this movement, bending stress is developed, and because of the shear force, shear stress is developed in the beam. The bending moment at any section tends to bend or deflect the beam, and the internal stresses resist its bending. So the process of bending stops when every cross section sets up full resistance to the bending moment. The resistance offered by the internal stresses to the bending is called the bending stress, and the relevant theory is called the theory of the bending. For the design purposes, a beam should be so designed that it should have adequate stiffness so that the deflection are within the permissible limit. So this is a beam, a simply supported beam. It will deflect like that due to the transverse load. Cantilever beam also deflect from fixed end to the free end. Now what happens there? Suppose this is on the right hand side, we have a beam. When the force is applied or the load is applied on that beam, the upper portion of the beam gets, after deflection, is in compression and the lower part is in tension. Or we can say that upper part of the beam in compression, or the top fiber is in compression and the lower part of the beam in tension. Bottom fiber in tension because the length increases, upper part in the compression because the length decreases. But there will be some axis in the beam where the stress changing from compression to the tension. That axis is known as the neutral axis. The layer which does not undergo any change in length is the neutral layer, and the line of intersection of the neutral layer with the plane of the cross section is the neutral axis. It passes through the CG of the cross section. So we can define deflection of beam as when a beam is subjected to the transverse load, it deflect or it will sag. The neutral axis, which was initially a straight line, now become a curved line. This line is called the elastic curve. Let us consider a cantilever beam and the load is applied on its free end. So see how it will deflect. It will deflect from the fixed end to the free end due to the load acting on the free end. Whenever a cantilever beam is loaded, it is deflected from its original position. The amount by which a beam is deflected depends upon its cross section and the bending moment. It depends upon the cross section and the bending moment. Let us visualize by this diagram. This is a beam and it will deflect like that. So clearly it is shown deflection by the y or the del x. Deflection is of the free end, from fixed end to the free end. The amount by which a cantilever beam deflects depends upon its cross section and the bending moment. So the line which was in the neutral axis, which was initially a straight line, now become a curved line. This line is called the elastic curve. The deflection of a beam is a vertical distance between a point on the elastic curve and the unloaded neutral axis. Now we will discuss about the theory of the simple bending. So before discussing, we have to take some assumption. First, the material is homogeneous and isotropic. What does it mean? A material is said to be homogeneous when it exhibits same elastic properties at any point in a given direction. Here is a figure in which I have made a number of points, and properties are independent of that point. At every point there is elastic properties, same elastic property. Now, what is isotropic? A material is said to be isotropic when it exhibits same elastic property in any direction at a given point. Or we can say that properties are independent of direction. That is, this is a point and the properties are same in every direction. We can say that properties are independent of the direction. In homogeneous, properties are independent of point. Second is the beam material is stressed within the elastic limit and thus obeys the Hooke's law. Hooke's law states that stress is directly proportional to the strain, whether it is shear stress, it is directly proportional to the shear strain, normal stress is directly proportional to the normal strain, and when we apply this, when we remove this proportionality sign, we use some constant like modulus of elasticity, modulus of rigidity. Now I will discuss about the bending and the section modulus. M upon I, moment upon moment of inertia, is F upon Y, where F maximum may be tensile or compressive in nature, and Z is the modulus of section modulus, which is equal to I upon Y, moment of inertia upon Y. It represents strength of the section. Greater the value of the section modulus, stronger will be the section. So I section has more moment of inertia. So so more the strength. Then T section. Then this I section. Then we have a square section, and then we have a circle. A square cross section with sides are vertical and horizontal sides are 41.4% stronger than a square with a diagonal under the bending. So moment is directly proportional to the strength. Section modulus is inversely proportional to the bending stress. When a beam is said to be uniform strength, when bending stress is same at every section along its longitudinal axis. So now we have some cases of movement: cantilever beam with movement, cantilever beam with point load, cantilever beam with UDL, and cantilever beam with UVL, uniform varying load. Now I will show some tricks to solve that question. The blue dotted, see the formula of blue dotted, this is actually a trick, not a formula. Slope at the free end is given by, in the first case, ml upon ei, then ml upon 2i, then ml upon 3ei, then ml upon 4ei. It is sequence wise: ei divided by 2i, 2ei divided by 3ei divided by 4ei. So you just calculate the moment at the free end or at the prop, and substitute it in this formula. So in the first case, cantilever beam with the movement, due to this movement at the free end, there is a movement at the fixed end, and is equal to the m. So we get a formula ml upon ei. We can do this question in some second. Now in the second case, due to the, if we apply a prop here, so the load, due to the load goes into the dead prop, so their movement is w into l, w into l. So formula is w l square upon 2ei. You just have to calculate the moment here. So in the UDL case, the entire length is equal to l. W l square upon 2 is the moment. You have to put that moment in the formula ml upon 3ei. We get w l square upon 2 into l divided by 3ei. So finally we get w l cube upon 6ei. And in the fourth case, ml upon 4ei. WL square upon 6 is the moment, is equal to the area of the dead triangle into the distance length, that is L. So we get WL cube upon 24ei. Now in the case of the deflection, formula is reaction at the prop divided by 3ei upon L cube. In every case, you just calculate the reaction at the prop. Deflection at the free end is, here the reaction at the prop is 3 by 2 ml divided by 3ei L cube. Sorry, this is not L square, this is L cube. In every case, this is L cube. Sorry for that. So we can write deflection at the free end is ml square upon ti 2ei Now in the second case, deflection equal to, it is a cantilever beam with the point load concentrated at a point. So here the deflection at the free end is equal to that W, the load acting on it. So W divided by 3EI L cube. Sorry, again here this is L cube, not L square. So we get WL cube upon 3EI. Now in the third case, we have cantilever beam with UDL. Here the reaction at the free end is 3 by 8 WL. The reaction at the deflection at the free end is WL4 upon 8 EI. We just put the value of the reaction at the probe. 3 by 8 goes in the free end and 5 by 8 in the fixed end. So you have to calculate the value. So as the load increases, we see, and in the fourth case WL 4 upon 30 EI. We see in the case of the slopes that when there is a point load, moment is ml upon, the slope is ml upon ei. In the second case ml upon 2 ei, and the third case ml upon 3 ei. We see the slope is continuously decreasing. As the load increases, the slope is continuously decreasing. This is also a trick you have to remember. So in every case you just know the reaction at the probe for to find the deflection. Friends, if you not know how to find the reaction at the probe, just write in the comment box, or I will make a separate video for that also. If you like this video, please share with your friends and subscribe the channel. Thanks for watching the video. Keep supporting, keep subscribing so that you will get the new notification. Thanks friend.